Okay, we'll start with this amplitude modulation. So we were done with the expressions, amplitude modulation. So I will repeat few things. So the expression for the amplitude modulation, we were having m of t as message signal, then you have carrier as c of t, and you wrote this expression for c of t as ac. AC is the amplitude of this, then cos of twice pi fct, right? So we have overall expression for the am signal, am of t, it is equal to ac 1 plus ka mt, then cos of twice pi fct. So this is the final expression for amplitude modulation. Yeah, amplitude modulator, where we have Ka as amplitude sensitivity, where this is equal to as amplitude sensitivity. Ka is equal to amplitude sensitivity of Am, right? No, now we will go for the spectrum analysis of Am, right? Spectrum analysis of Am. So you can understand also the concept of modulation here. So suppose, are you getting me? Anybody having any doubt till now?
No, sir.
Okay. Concept of modulation.
Okay.
Then from using the same concept, you can draw the amplitude modulation graph and its spectrum. Suppose we're already done with this. I will repeat few things. Suppose we have a modulating signal. This is my modulating signal. So modulating signal is a rectangular shape, but you can say it's from minus tau to tau, and this is t, your time domain. And you can say tau by 2 is minus tau by 2, and its value is 1, and this is your m of t, m of t. And then if you will write spectrum, a rectangular shaped symbol in time domain, it will be always sync function that you have already studied in Fourier transform. It will be sync function like this, right? If you will say simple general x of omega, yeah, sorry, this is m, so this will be your m of f. So this is your f. It will be like this. If you will draw the mod of this, then mod of this will be, you will have all the positive values, only negative values you will be having 0. So if you will see like this, so this is its value. So all the negative values will be cancelled. Why? Because you will take the mod of this. So negative will be converted to positive. All the negative values, you will not represent negative values. So you have all the positive values here. It will be like this now. Now, one of the point which you remember that 99.9% of the power will be represented by the main lobe. It will represent 99 point of this power, or 99.9% of information is represented by the main lobe. And side lobes, they are just causing the interference to the nearby bands. So you will pass this through a low pass filter, and after that you will get the value like this. Oh, so this is the value you will get. So this is m of f. So this is f, right? All the other secondary lobe values, these values will cancel out, because when you pass this through a low pass filter, you will get only the primary lobe, main lobe, and this will represent all the information. Point one information will be represented by the side lobes, and that's negligible. You can cancel out these lobes. So in general, whenever you will be having time domain signal like this rectangular time domain signal, it will be always represented by this one lobe main lobe. So this is t by tau by 2, this minus tau by 2, this is 0, and this is your 1, and this is m of t, and this will be m of f. So in general, whenever you have rectangular signal, you will represent by this. Somebody will tell you what's the reason why you represent by this. It's actually a sync function. You will say all the secondary low values, they represent 0.1%, yeah, 0.01% of the information, and that information is negligible. So you can represent by this so that it carries the maximum, so that it will not waste any spectrum. So this will be 1 by tau, and this will be minus 1 by tau, right? So this is the value of this. Now suppose, and you just remember this tau value will be in 1 microsecond, you would say, or 1 millisecond. It can be one. Similarly, if this is in microsecond, so 1 by 1 divided by 1 microsecond, so this will be in 1 megahertz minus 1 megahertz to 1 megahertz. If this is in millisecond, so this will be minus 1 kilohertz to 1 kilohertz. So you just remember this thing, right? Okay. Then you can say that baseband signal component significant low frequency component irrespective of high frequency component. Now you just remember this. Now I will draw the graph of this carrier signal C of t. Suppose carrier signal, everybody will be able to represent the graph of this. So C of t is a cos of 2i pi fct. This is just a sinusoidal signal having a frequency fc. So this, can you represent this graph? So this will be your 1 minute, 1 minute. Okay, so it's not exactly, but this is sinusoidal. Just you can see. So this is your cos. I'm not able to represent this properly, but you can see this is cos signal. Its value will be at 0, 1. Maximum amplitude is AC, and this is minus AC amplitude, right? Anybody having any doubt? Hello?
No, sir. No, sir.
Why you are not responding? What had happened to people? Please respond. So this will be from its value we have already done with this. Its spectrum will be at 2 points. This is AC by 2, right? Fourier transform we have done this, and this is also AC by 2, and this value will be FC, and this will be minus FC, and this is 0. This is the spectrum of C of t. So you can say this is C of omega ur. So this is your F. So it has you can say from this graph, you can say that it has only one frequency component that's present at FC. So that is the reason this is also called as single tone frequency signal. Yeah, single tone signal, single tone signal, right? So this is single tone signal. Now in
Sir.
right, in modulation, what you do, you multiply m of t with c of t. M of t is multiplied with c of t. The resultant will be m of f will be multiplied by c of omega. Now we will see what happened. So now you will do modulation s of t is equal to, you just say that this is m of t is multiplied by c of t. Whenever you multiply these two signals, this signal, first one, then second signal, you will, because after t by 2, you have value 0, because this is 0 value. So similarly, up to t by 2, you will get the same value as this cos. After that, you will get 0 value. So whenever you multiply these two signals, what you will get resultant? Just draw the graph. So you will get the signal same as this is tau by 2 minus tau by 2, and this is tau by 2. After that, because in m of t it is 0, 0 multiplied by this will be 0. So this will be your signal value. Done.
Yes, sir.
Done like this. This is your, whenever you multiply the message signal with your carrier signal. Why? What was the reason this value will be? This value will be 0. Why? Because in m of t, this value is 0. Because m of t value is from 0 to tau by 2 minus tau by 2 to tau by 2. After that, this is 0 value. This is 0. Whenever 0 is multiplied by any value, you will get 0. So after that, you will get 0 value. And this is in time domain. Similarly, whenever you multiply these two signals, we have already discussed one of the property that's called modulation property. Modulation property, we see that whenever any sinusoidal is multiplied by some signal, you get then the same frequency signal band. Anybody remembers that modulation property? So you can use here modulation property. I will draw the graph, then we will little bit repeat the same property here. So whenever you get this graph m of t will be shifted here, and this value will be minus fc. Similarly, this will be shifted here, and this is fc. So you have fc here minus fc and fc, and this value will be something fc plus fm. That means frequency of your original signal, and that is highest is 1 by tau, and this is fc minus 1 by tau, right? So this is minus fc plus 1 by tau, and this is minus fc minus 1 by tau, and 1 by tau will be some fm frequency, something like that. So this will be the final signal. Why do you get this signal actually? And at fc there will be your component present, that is ac by 2. Similarly, you have here ac by 2. Now somebody will tell how this spectrum will come from this, because mt, suppose mt signal, its frequency is, its Fourier transform is m of f. Whenever you multiply m of t with cos twice by fct, then you will get m of f plus fc, then plus m of f minus fc, right? And this will be 1 by 2, and this will be also 1 by 2. So multiply this by AC, then you will get AC by 2, then you will get here similarly AC by 2. So that means spectrum M will be shifted towards right, and it will be shifted towards left. It will be shifted towards right. This is right shifting, and this is left shifting. And then AC component will be present same, AC by 2. This AC by 2 is the component. This is AC by 2. And then you will get the same spectrum two times because of symmetry. Are you done with this? Anybody getting some point? Because this is the original spectrum of M of F. Then M of F will be shifted from 0. This is 0 value, 0 to FC. So this will be here spectrum. And similarly, it will be shifted towards minus FC. And that's the reason we have this spectrum. Anybody having any doubt, please tell me. Junaid?
No, sir.
Junaid बताएगा. Look, if you have M of T, this is very important property. Suppose you have M of T. It can be any signal in time domain. It's in frequency domain. Let this be M of F. Then whenever you multiply M of T with AC cos of twice by FCT, what will be the value? Before going for this, you convert this to e raised power something formula using Euler's formula. So you have, can anybody tell me what I will get? This is AC M of T e raised power j twice by fct, then बताओ, plus e raised power minus j twice by fct whole divided by 2. What I will get? Tell me. Tell me what I
सर
will get.
बेस सेम हो जाएंगे
हाँ,
और
नहीं नहीं
टी
बेस नहीं, अरे भाई, m of t का इस value is m of f, right? Now multiply this first part with this, what you will get? You will get ac by 2, then you have m of t e raised power j twice by fct. Similarly, you have ac by 2 m of t into e raised power minus j twice by fct. Anybody, since m of t when converted to Fourier transform, it's m of f. Now multiply ac by 2, it's constant. It will be similarly ac by 2 here and ac by 2 here. Now, whenever you multiply with this exponential, what you will get? You will get simply ac by 2. Then we have m of f, this minus fc, f minus fc. This is the value of the first one. So second one, it will be plus AC divided by 2 m of f plus fc. These two. This is the value of AC m of t cos of twice by fct. Done. Now same case I have shown here. We have m of t. This is the frequency spectrum of this. Now we have cos t carrier, then this is the frequency spectrum of this. Now, whenever you multiply these two using modulation, you will get the spectrum shifted by fc from 0 to fc here, and similarly from 0 towards left by minus fc. And this is the final value I'm getting. Same will be the case for amplitude spectrum. So there are two bands here. One will be upper side band, this one will be upper side band, this one will be lower side band, and this is the frequency of this. So we have two bands, and what will be the total this value of this frequency range? Can anybody tell me? You have fc plus 1 by tau minus fc plus 1 by tau plus 1 by tau. Fc and fc cancel, so you have 2 by tau. Total frequency of this will be 2 by tau. This is the frequency band occupied by our signal. 2 by tau is the maximum frequency band occupied by our signal. Now you can use the same analogy for your amplitude spectrum. So we will go for the spectrum analysis of AM, analysis of AM. Suppose we have m of t in a signal, let its frequency spectrum be like this. I'm assuming this, right? I'm assuming this. So we have omega, this is minus omega, this is 0, and this is your m of f. So this will be your f, or you can say omega or f, whatever. Now you, whatever you do, you will have cos t. Cos will be equal to carrier, that's equal to cos twice by fct. Then you have this signal, you have 2fc and another one will be at minus fc. अभी बताया ना मैंने, अभी तो किया है ये cos का, and mt ka value this. Now, whenever you multiply these two signals, that means st, mt, and ct, tell me the value of the spectrum. Can anybody tell me what the graph will look like? Can anybody tell me the graph? Tell me, please. दो आएगा, एक यहाँ पे, एक कहाँ पे, fc के पास, राइट? दूसरा कहाँ पे आएगा? अभी किया हमने ये सारा. दूसरा आएगा माइनस fc, राइट? fc पे आएगा हमारा एक कंपोनेंट जो कि था यही AC/2। अगर हम AC/2 लिखते हैं यहाँ पे, AC AC/2, similarly we have here value that's called AC/2. This is FC, this is minus FC. Now what is this value? This value will be FC plus omega. What is this value? This value will be FC minus omega. So total spectrum occupied by this is higher component minus lower component, that's 2y omega. Similarly, what will be this value? Will be minus Fc plus omega. What will be this value? It will be minus Fc minus omega. And total range occupied by this is 2y omega. And this is called as upper side band. We have two bands. One is upper side band, and then another one is lower side band. Similarly, here this is lower side band, and this is your upper side band. Upper side band. Done. So bandwidth of AM. This is called also double side band full carrier. AM is also called as double side band full carrier. So its bandwidth from the spectrum we conclude is twice m, where omega is the highest frequency component of the modulating signal, of the modulating or message signal, of the modulating signal or message signal. Highest frequency component is omega. Bandwidth will be always twice omega. So upper side band, it always exists above FC. Lower side band always exists below FC. So we can say, conclude that bandwidth of double side band full carrier or AM is 2 omega. There are two bands. One is upper side band, another one is lower side band. So we will study. There are certain mm, drawbacks in this case. It occupies more bandwidth. In order to reduce the bandwidth, we will use the single side band instead of two bands. We will use a single band because both the bands contain the same information. What's the need for transmitting both the bands? We can transmit a single band also, and still information will be remain intact. That we will study tomorrow and also go through this. Anybody having any doubt, please tell me. Okay then.